On September 13th, 2017, a spacecraft traveling at over 70,000 miles per hour pointed its cameras one last time at the rings of Saturn, at the frozen moon Iapetus, at the orange haze of Titan, and took its final pictures. 2 days later, it was gone, burned alive inside a planet 900 million miles from Earth. The world watched, scientists cried, and then the data was archived. The mission was declared complete. The books were closed. But here's the thing nobody told you. Those final images were not finished speaking. Not even close. Because right now, in 2025 and 2026, those archived transmissions from a dead spacecraft are producing discoveries so staggering, so unexpected, so genuinely world-altering that researchers are struggling to find the right words to describe what they're looking at. We're not talking about upgraded software cleaning up old photos. We're talking about findings published in journals like Nature Astronomy and the Planetary Science Journal that are actively rewriting the rules of what we thought was possible in our own solar system. Findings that directly answer the oldest question human beings have ever asked. And it all starts with those final images. Stay with me, because what Cassini saw in its last moments is only now beginning to make sense. To understand why this matters, you have to understand what Cassini actually was. Not just a spacecraft, not just a machine. Cassini was the most ambitious planetary explorer ever built by human hands. Launched in October 1997 with a Huygens probe attached to its side, it spent 7 years crossing the solar system before arriving at Saturn in 2004. What followed was 13 years of continuous discovery in a place our telescopes could barely see clearly. Over the course of its mission, Cassini sent back 453,048 images. It completed 294 orbits around Saturn. By the time it died, it had traveled 4.9 billion miles. It discovered liquid methane seas on Titan. It found geysers of water shooting from the south pole of Enceladus. It detected the building blocks of life hiding inside those geysers. It mapped Saturn's magnetic field. It flew through the ring system itself. And in doing all of this, it fundamentally reshaped what we know about the outer solar system. But scientists always knew that Cassini's data was so rich, so dense, so complex that it would take decades to fully understand what had been collected. What they didn't fully appreciate was how right they were. Because the revelations coming out of Cassini's archive right now aren't minor updates. They're seismic. The final images sit at the center of all of it. Let's talk about those last moments in detail, because what happened during the grand finale is genuinely one of the boldest things any space agency has ever attempted. In April 2017, with Cassini running low on fuel, NASA made a bold decision. Rather than letting the spacecraft drift and potentially contaminate one of Saturn's moons by crashing into it, they designed a controlled death dive, but not before doing something extraordinary. For 22 weeks, they flew Cassini through a region of space that no human-made object had ever entered before, the roughly 200-mile gap between Saturn's innermost ring and the top of its atmosphere. Nobody knew what was in that gap. Nobody knew if the spacecraft would survive. But they flew it through anyway. 22 times, instruments running at full capacity, cameras firing, sensors wide open, collecting data from a place science had never touched. Then, on September 13th, 2 days before the final plunge, the cameras captured their last images: Enceladus, Titan, the rings, Saturn's northern hemisphere. These images were transmitted to Earth and archived. They looked stunning. They looked complete. But the instruments that were measuring, sniffing, tasting the environment in that gap, those results were so unusual, so unexpected, that scientists initially suspected their own equipment had malfunctioned. Here is what was hiding in that gap, and in those final transmissions, only now being fully decoded years later. When Cassini flew through the space between Saturn's rings and its atmosphere, its ion and neutral mass spectrometer, essentially a device that identifies chemicals by smell, picked up something that made the entire science team stop and stare at their screens. Complex organic compounds were raining down from Saturn's rings into its atmosphere. Not simple molecules, complex ones, hydrocarbons, carbon-based chemistry, falling from the rings at a rate of up to 10 tons of material every single second. Scientists already knew about a phenomenon called ring rain, where particles from Saturn's rings trickle down into the planet. But the scale of what Cassini measured in that final stretch was completely different from any prior estimate. The rings weren't slowly leaking. They were actively pouring their contents into Saturn at a rate that means the rings, as we know them, could disappear entirely within 100 million years. That single number changed our entire understanding of what Saturn's rings are, where they came from, and how long they have left. One of the most iconic features in the entire solar system may be a temporary thing, a short chapter in a much longer story. And Cassini's final orbits gave us the first real numbers to understand that. But the organic compounds were just the beginning. During those same final grand finale dives, Cassini made another measurement that sent shockwaves through the physics community. Saturn's magnetic field is strange. Every other planet in the solar system has a magnetic field that's tilted relative to its rotation axis. Earth's magnetic north pole isn't the same as geographic north. Jupiter's magnetic field is tilted. Even Uranus and Neptune are dramatically tilted. But Saturn's magnetic field is almost perfectly aligned with its rotation axis. The tilt is less than 0.1 degrees. That's impossibly, unnervingly precise. And this matters enormously, because standard planetary physics says a magnetic field must be tilted to sustain itself over billions of years. A perfectly aligned field should collapse. It shouldn't exist. Yet there it is. Cassini measured it directly during its final dives, confirming just how extraordinary the alignment really is. Scientists are still debating what this means. Some believe there must be a layer deep inside Saturn, a hidden shell of some kind that's canceling out what should be a tilted field. Others think our models of planetary magnetic field generation are simply wrong, and Saturn is telling us something we don't yet understand. Cassini gave us the clearest measurement of this mystery ever taken, and the mystery only deepened. Those final transmissions handed science a puzzle it will be chewing on for generations. And then there's the hidden halo. In December 2025, a paper published in the Planetary Science Journal revealed something that had been buried in Cassini's grand finale data for years. Saturn's rings, the ones we see as a flat, thin disk in photographs, aren't actually flat or contained. During the final orbits, Cassini's cosmic dust analyzer detected a vast, invisible halo of dust particles extending up to 3 times Saturn's radius above and below the ring plane, 3 times the planet's radius. This halo had never been seen before because it was invisible to telescopes. It took a spacecraft physically moving through it to detect it. The rings of Saturn, already the most dramatic structure in the solar system, are even larger and more complex than any image has ever shown. Cassini flew through the outer edges of this halo and sent back the data, and it took until 2025 for scientists to fully process and understand what that data was actually saying. The picture of Saturn sitting in your head right now, the one with the beautiful rings, is incomplete. The real Saturn is surrounded by a ghost-like cloud of material reaching into a region we never thought to look in. And we only know about it because of what Cassini captured in those final months. But nothing, and I mean nothing, in Cassini's archive compares to what scientists pulled out of the Enceladus data in 2025. This is the one that stopped the world. This is the discovery that changed the conversation about life in the universe. Enceladus is a small moon. You could fit it inside the continental United States. It's covered in bright white ice, and it orbits Saturn in less than 33 hours. When Cassini first arrived at Saturn in 2004, Enceladus was considered a minor curiosity. By 2005, everything had changed. Cassini discovered geysers, enormous jets of water, vapor, and ice particles blasting from cracks in the moon's south pole, shooting thousands of kilometers into space and feeding material directly into Saturn's E-ring. Those geysers told scientists something extraordinary. Beneath that frozen surface, Enceladus has a liquid water ocean, a global, salty ocean kept warm by the tidal forces Saturn exerts on the tiny moon's interior. Over the following years, Cassini kept flying through those plumes, tasting what was inside. It found salt. It found silica particles that pointed toward hydrothermal vents on the ocean floor, the same kind of structures on Earth that many scientists believe gave rise to the earliest life. It found simple organic molecules. Each discovery was astonishing on its own. But in 2025, when researchers went back to Cassini's archive with new analytical tools and fresh eyes, what they found went far beyond anything previously announced. In October 2025, a team led by researcher Nozer Khawaja, working with archives from Cassini's cosmic dust analyzer, published a paper that drew a direct line between the chemicals inside Enceladus and the chemistry of life on Earth. The key was a distinction nobody had made clearly before. Most of the organic material Cassini had found in earlier analyses came from ice grains circulating in Saturn's E-ring, grains that are sometimes hundreds of years old and have been baked by radiation. When Khawaja's team reanalyzed fresh plume grain samples using more sophisticated methods than were available when Cassini was active, what they found was stunning. The fresh plume material contained complex organic molecules that had never been identified in the older E-ring data: esters, ethers, alkanes, nitrogen, and oxygen-bearing compounds. These aren't simple space chemicals. On Earth, esters and ethers are components of lipids, the molecules that form the membranes of every living cell. They're part of the basic structural toolkit of biology. Their presence doesn't prove that life exists inside Enceladus. But it proves something almost equally remarkable, that the chemistry inside that hidden ocean isn't simple. It's complex. It's active. It's producing molecular structures that on our planet are the precursors to the most fundamental components of living things. The paper was published in Nature Astronomy in November 2025, and the reaction from the scientific community was immediate. One researcher described it as simply phenomenal. Another called it the clearest signal yet that Enceladus is not just wet, it's chemically alive in ways that are compatible with biology as we understand it. Frank Postberg, one of the study's co-authors, put it plainly. The complex organic molecules Cassini detected in Saturn's E-ring aren't just a byproduct of long exposure to space. He said they're readily available inside Enceladus's ocean. That sentence matters. It means the ocean is actively producing these compounds right now. Whatever chemistry is happening under that ice isn't ancient or passive. It's ongoing, and it's producing molecular complexity at a level we didn't expect to find this far from the Sun. Enceladus, this tiny, frozen, overlooked moon, may have an ocean beneath its surface that's more chemically rich and more biologically promising than anything we've found elsewhere in the solar system. A moon of Saturn doing chemistry that life does on Earth. That's what Cassini's final transmissions contained. That's what took years to fully read. Now, let's talk about a parallel discovery that came from re-examining the data Cassini collected about Titan, Saturn's largest moon, during that same period. For years, scientists believed Titan almost certainly had a large, deep ocean of liquid water hidden beneath its frozen surface, similar to Enceladus. The moon is massive, larger than the planet Mercury, wrapped in a thick nitrogen atmosphere with lakes of liquid methane on its surface. Scientists figured that with all that internal heat and tidal activity, a subsurface ocean was practically guaranteed. In September 2025, a new analysis of spacecraft data turned that assumption on its head. The re-examination of measurements taken more than a decade earlier suggested Titan probably does not contain the massive liquid water ocean previously theorized. Its interior appears to behave differently than expected. This is the other side of what Cassini's legacy keeps delivering. Not just confirmations of what we hoped, but corrections of what we assumed. Science correcting itself on the basis of better analysis of the same data. The universe pushing back against our models. Titan is still one of the strangest and most fascinating places in the solar system, but it's stranger than we thought in ways we're still untangling. There's also the matter of Mimas, one of Saturn's smallest moons, looking almost comically like a space station with its giant crater. Mimas was considered one of the most geologically dead objects in the Saturn system. No geysers, no signs of internal heat, nothing. Just a frozen, cratered ball of ice. In February 2024, scientists analyzing Cassini's data on Mimas's orbital motion. The tiny wobbles and variations in how it moves around Saturn made an announcement that flipped that picture completely. Mimas has a liquid water ocean beneath its surface too. A young one, formed somewhere between 5 and 15 million years ago, making it essentially newborn on geological timescales, and nobody had any idea it was there. The surface of Mimas looks ancient and dead. Nothing about it externally suggests an active interior, but the orbital data Cassini recorded told a different story. The moon is wobbling in a way that only makes sense if there's a large body of liquid water sloshing around inside it. A hidden ocean on a moon that looked like a dead rock, found in data Cassini collected years before anyone knew what to look for. This is the pattern of Cassini's legacy. You look, you find something, you archive it, you come back years later with better tools and a deeper understanding, and the data hands you something you completely missed the first time. And then there's the question of what all of this means together. Stand back and look at the full picture Cassini painted. A system where multiple moons have liquid water oceans beneath their surfaces, including moons that show absolutely no obvious external sign of it. A planet whose rings are actively raining complex organic chemistry into its atmosphere at a rate of thousands of tons per second. A magnetic field that defies our models of planetary physics. A hidden dust halo surrounding the rings and extending into space far beyond what any telescope ever detected. And floating above the south pole of a small frozen moon, jets of water carrying complex organic molecules, esters, ethers, nitrogen compounds, the kinds of chemicals that on Earth build cell membranes and drive the reactions of life, shooting straight out into space. All of this was collected by one spacecraft during 13 years of exploration and a final suicidal dive into the planet's atmosphere. All of this is still being decoded. All of this is still being published. The mission ended in 2017. The discoveries didn't. The European Space Agency has already named Enceladus one of its highest priority targets for a future mission. ESA is studying a spacecraft that would land on and sample the south polar region directly to collect that plume material from the surface itself rather than from orbit. NASA's Europa Clipper is currently flying toward Jupiter's moon Europa, another candidate for subsurface life, using the same principles of ocean-moon exploration that Cassini pioneered. The entire field of astrobiology, the study of life's potential beyond Earth, has been reshaped by what Cassini found. Scientists now talk about a class of worlds called ocean worlds, moons with liquid water hidden beneath their surfaces as serious targets for life detection. Enceladus, Europa, Ganymede, Titan, Mimas. 5 worlds in the outer solar system where liquid water may exist right now. 5 chances. Before Cassini, we had suspicions. After Cassini, we have evidence. And the latest round of papers being published in 2025 and 2026 isn't wrapping that evidence up. It's opening new doors. Here's what strikes me most deeply about all of this. Cassini wasn't looking for life. It wasn't designed to detect life. Its instruments were built to measure magnetic fields and chemical compositions and ring structures and atmospheric dynamics. It was a generalist explorer sent to a system we barely understood, carrying tools designed to measure what we expected to find. And yet, in its final transmissions, in the data from those last 22 orbits through the gap, in the archived measurements taken during a deliberate death dive, it found molecules that form cell membranes. It found hidden oceans inside moons that looked dead. It found rings evaporating into a planet at impossible rates. It found a magnetic field that shouldn't be stable, but is. It found a dust halo 3 times the size of the planet itself. None of these were the things it was sent to look for. All of them were sitting in the data, waiting for us to develop the understanding and the tools to recognize what was there. The archive still isn't finished. Scientists estimate that the full scientific yield of Cassini's data will take another decade or more to fully extract. Every year brings new papers. Every new paper brings new surprises. The spacecraft is gone, vaporized in Saturn's atmosphere 7 years ago. But in a very real sense, it's still working, still transmitting, just slowly, through the patient, careful, years-long work of researchers sitting at computers running new analyses, applying new understanding to old numbers, and finding things that were always there, invisible until now. Cassini's final images stopped the world, not because of what they showed on the surface, not because of the visual beauty of Saturn's rings or Titan's hazes or Enceladus's jets. They stopped the world because of what was hidden inside them. Information that took years of scientific progress to be ready to read. Messages written not in patterns or codes, but in the language of chemistry and physics. In organic molecules shooting from an alien ocean, in the wobble of a moon's orbit, in charged particles falling along magnetic lines into a gas giant's sky. Cassini saw all of it. It recorded all of it. And piece by piece, year by year, we're finally beginning to understand what it was trying to tell us. We sent a machine to the edge of our solar system, and it came back with the strongest evidence in human history that we may not be alone in our own backyard. The final images didn't close the story. They started a new one. And we've only just begun to read the first chapter. Think about what the new Enceladus findings actually require to be true. For those organic molecules, the esters, the ethers, the nitrogen-oxygen compounds, to be shooting out of the moon's geysers in the concentrations and variety Cassini measured, the ocean that produced them can't be a simple, cold, quiet body of water. It has to be chemically active. It has to have energy inputs, almost certainly from hydrothermal vents on the ocean floor, vents generating heat and driving chemical reactions in the water above them. The silica particles Cassini detected earlier in the mission already pointed toward this. Silica of the specific size and type Cassini found can only form when water at very high temperatures contacts rock. That means hot water. That means hydrothermal circulation. That means the ocean floor of Enceladus isn't a cold, dead plain of rock. It's a geologically active boundary where water and rock interact at high temperatures, producing exactly the kind of chemistry that on Earth happens at the hydrothermal vents on our own ocean floors. And those vents on Earth, the ones at the bottom of the Pacific and Atlantic and Arctic oceans, are not barren. They're teeming with life. Organisms that need no sunlight, no photosynthesis, no connection to the surface world at all. Life that feeds entirely on the chemical energy produced by hot water meeting cold rock. Chemosynthesis instead of photosynthesis, life built on geology instead of sunlight. If that kind of life exists on Earth, in environments completely dark, completely isolated from the surface, completely dependent on internal heat rather than solar energy, then the question of whether something similar could exist inside Enceladus isn't science fiction. It's a serious scientific question with serious scientific weight behind it. And Cassini's data is the reason we're asking it. There's one more thing worth saying about what Cassini's final transmissions represent. Not as data, but as an idea. We built a machine. We launched it into space. We aimed it at a distant planet. We flew it for 20 years. We programmed its death. And in the final weeks and days and minutes of its existence, as it dove through unexplored space and fell into a planet's atmosphere and vaporized into nothing, it was still working, still measuring, still sending. The last signal from Cassini reached Earth on September 15th, 2017, at 7:55 in the morning, Pacific time, 83 minutes after the spacecraft itself had already ceased to exist. Because that's how long it takes a signal to travel from Saturn to Earth. For 83 minutes, Cassini was already gone, and nobody knew it yet. The data was still flowing. The transmission was still arriving. The machine had already died, and its voice was still being heard across 900 million miles of empty space. That image, a dead spacecraft still speaking, still teaching, still revealing across nearly 1 billion miles of darkness, isn't just poetic. It's the most accurate description of what the Cassini mission continues to be. Even now, in 2025 and 2026, researchers are still listening to what it said, still finding things in what it recorded. The machine is gone. But the knowledge it gathered, packed into 453,048 images and terabytes of instrument data and chemical readings and magnetic field measurements, that knowledge is still unfolding, still speaking. And what it's saying, about hidden oceans and organic chemistry and evaporating rings and impossible magnetic fields and dust halos and geologically active moons is more extraordinary than anything the scientists who designed Cassini dared hope they'd find when they launched it into the dark in October of 1997.